Hello, everyone. Thank you for joining today, and welcome to the first seminar of the series of space engineering seminars at the Department of Aeronautics. I would like to have the pleasure to introduce today the first speaker, who is Mike Lindsay from Astroscale. So Mike is the Chief Technical Officer for the Astroscale Global Group, and is based in Tokyo, Japan. His experience includes not only areas such as mission design, space systems engineering, and spacecraft operations, but also regulatory affairs and spectrum management. Bringing a passion for orbital sustainability, Lindsay joined Astroscale in 2019 after working in NASA, Google, and OneWeb, where he designed their constellation of satellites with attention paid to the necessity of an adequate deorbit plan. Mike, the floor is yours.
Thank you very much. Just going to clip this here. Yeah, thank you very much for that kind introduction. It's an honor to be the first speaker in the seminar series. Worked out really well that I could be here in person. So yeah, thank you for the opportunity. As David mentioned, my career has brought me from public sector to private sector. Worked for OneWeb for a while. And throughout my career, I became more and more aware of space debris and the problems of sustainable development in space. So it's been this path that has led me to where I am today at Astroscale. So there's a lot of passion within our company that is shared between our employees. So it's well, it's been a really good position for me. But I'd like to talk a little bit more about the state of the space environment, what Astroscale is doing to contribute to that, and also talk a little bit about the ELSA-d mission that is currently in space right now. So give an update on those operations and what they mean for the future. Just focus here. Okay. I probably don't need to explain this to the group here, but I think we're all well aware that space technologies and architectures affect our daily lives. We're often relying on space technologies without even knowing it. I do like to say that space isn't really part of our biosphere. It's not a biome right now, but it is really important for the monitoring, data collection, informs our actions on climate change. There's agricultural monitoring. We can see deforestation happen there. So it's really critical infrastructure for managing our planet. So it's worth protecting. It's worth making sure that our activities are sustainable there. And as we also know, our utilization of space is steadily increasing. We're seeing more and more activity in space. This has been enabled by lower cost access to space. We're seeing more launch vehicles, lower prices, space components and hardware becoming more cost effective. And a lot more players are able to access space, which we think is great. A lot more diversity in the ideas and applications and backgrounds that are really promising for space development. And if you just look at some of the numbers, yeah, in 2020, there's only about 4,000 satellites in orbit. And we're looking at thousands of satellites being launched over the next few years. The number there on the right-hand side is predict an average of almost 1,000 satellites every year for the next several years. And I think we'll continue to be surprised by those numbers as they increase. When I started my job at OneWeb back in 2015, I remember being a little nervous about being public with our idea to launch. At the time, our proposal was about 882 satellites in the constellation. And we actually kind of reduced that number to 720 to make it more palatable to the public and regulators. But then shortly after, SpaceX announced 4,000 satellites and Amazon 3,000 satellites. And now numbers that are in the tens of thousands don't actually seem that ridiculous to propose, which is a complete paradigm shift from even 5 years ago. So this is a new trend in space. And I'm actually going to contradict myself. I said that space is not a biome, but we're seeing that more and more space tourism is gaining a lot of momentum as well. So we'll have more humans in space, and so making sure that that environment is safe for travel and utilization for valuable assets is important for development. So the question is, are we being sustainable? Is space sustainable today? Unfortunately, depending on your definition of sustainability, we're not showing good trends right now. The amount of space debris is steadily increasing, and there are a number of studies that show that if we kind of cut our space activity right now, we didn't launch any more satellites, we would still see the amount of space debris increase over the long term. This is because we have a lot of derelict objects, a lot of heavy, massive objects up there that are uncontrolled, and over time, there's a very non-zero probability that these objects will collide with each other, collide with other space assets, and at these hypervelocities, we have an impact that is energetic enough. You have complete catastrophic fragmentation, creating debris clouds that then go on to pose a risk to further assets in space. Of course, the off-reference theory is the Kessler syndrome, which is really just that one collision can spur a follow-on collision based on the debris that results from the prior one. People think that the Kessler syndrome is already begun because we are seeing collisions that go on to then damage other spacecraft. So unfortunately right now, if we carry on business as usual, we're going to find ourselves in a situation where we can no longer access space in the same way we do today. And so we're not setting ourselves on a good sustainable path. And that risk is something that we really need to be aware of, we need to quantify, we need to mitigate it. I'll just kind of focus on some of where the risks are coming from. Right now, we have the best understanding of objects that are 10 centimeters and greater in diameter. We can track these from ground-based radars and optical systems. We have a decent idea of where they're going in their orbits. We also know that a collision with an object that big is definitely going to be serious for the environment. So we build a lot of our systems and capabilities in the space industry to avoid and minimize those types of collisions. The next class down, 1 to 10 centimeters, is more difficult to track. In fact, we really don't have technologies widely deployed that can track and monitor these objects. And the unfortunate thing is that there's about 20 times more of these objects than there are greater than 10 centimeters. And these objects still pose a significant risk to a spacecraft. So a spacecraft that's a couple hundred kilograms could be fractionated by an impact of an object, 3 or 4 centimeters in diameter if it's made of a solid metal. So we have a significant portion of the risk that we don't fully understand, and we have no way to really remediate that risk. And then when you get to the micro objects between 0.1 and 1 centimeter, that is something that we can mitigate using things like shielding on our spacecraft, building more robust systems to withstand those impacts. But that 1 to 10 centimeters is a real problematic area. Sometimes you'll hear terminology, the lethal untrackables. You can't avoid it, but it's going to be lethal for your space satellite. So what do we do about that problem? Unfortunately, it's not really cost effective right now or today to go after each and every one of those pieces. They're spread out among a wide variety of orbits. They're difficult to track, and the delta V to get from one object to the next is prohibitive. So the best solution is to prevent their creation in the first place. The creation comes from breakups of satellites, explosions of components, be it batteries or pressurized vessels on board, or collisions of larger objects. So if we were to remove larger objects from orbit before they become small debris, then that's one way to remediate that risk. Just another more detailed look at where debris is today and how it's evolving. You see some, I guess, focus on the red line as the most recent data on where space debris is. But you see the red and blue lines are peaking right around 800-kilometer altitude. There were a couple of events that happened there. There was the ELSAd test that was an intentional test of anti-satellite capabilities that created a debris cloud there. The Iridium Cosmos collision, 2009 happened right around 800 kilometers. So that's why you're seeing these very large peaks in the distribution of objects in space. What's not shown in this plot is orbit inclination. But there's actually a high concentration of space debris in sun-synchronous orbits. And so what's unfortunate is that the most highly utilized orbits are the ones where there's the most debris right now, in terms of a lot of science applications. For communications, it's a little different story. For example, OneWeb is deploying at 1,200 kilometers, which has low density in terms of orbital debris, but debris that lingers there, debris that is created there will be there for well over 1,000 years. And I think, I'm pretty sure this spike here down at 550 is due to the Starlink constellation. They're deploying their satellites. Given recent news about the Kuiper constellation, probably be seeing another spike slightly above that, around 610, 630 is, I think, where they're deploying a lot of their satellites. So yeah, this goes back to the point where we're going to see this distribution continue to increase. I think this is total number of effective objects. And if those objects remain intact, controllable space objects, then that's not a bad scenario. That means we're efficiently utilizing space in a safe manner. But the real problem is when those objects become space debris and poses that risk to everybody across all of these orbits. So why are we having such a problem with the creation of space debris? Why are we not being sustainable? It's really kind of a historic attitude that we've had. I guess humans have not always been the best at thinking long term, making sure their industries and activities are sustainable. And space, unfortunately, hasn't been much different. There's always this notion that space is big. And if we just leave spacecraft in orbit, it's not really going to be an issue because the probability that that object is going to collide with something is just so minuscule, it's not worth even tracking or thinking about. So we've had this one-time use and throwaway culture around our launch vehicles and our spacecraft. And a lot of that has been driven by a technological necessity, really. Once you launch a satellite, it's extremely expensive to go up and service it or fix something. And so once you launch it in space, you just kind of want to do its job for 20 years or so. You don't want to have to worry about anything. But once that object is done, there's no refurbishment, there's no recycling, no repurposing. And most of the time, at least historically, when we're done with a spacecraft, we don't even dispose of it properly. The post-mission disposal rates historically have been well below recommended guidelines that have come from various bodies who are trying to develop best practices. I'll say, a few years ago that was outlined to be 90%. So they're saying that 90% of satellites that are in orbit should be brought down within 25 years. Now, because of the increasing number of satellites being proposed, everyone's saying that, okay, 90% is not enough. Maybe we need to be at 99%. And maybe it shouldn't be 25 years. Maybe it should be 5 years. I suppose picking a percentage, I'm just going to insert my personal opinion here. If we pick a percentage, it's always going to be lagging behind technology. We're always going to be trying to refine that percentage. We think the metrics should be driven more about the absolute impact to the environment. If you have a more direct quantification and management of what is happening to the environment, then you can have regulations that are much more effective. But what we're trying to do at Astroscale is unlock this new paradigm in the space industry. And that is through in-orbit servicing, the ability to go up and rendezvous with a space asset and perform a service. And this kind of unlocks two features. One is it unlocks more sustainable behavior, because now we can remediate space debris. We can remove objects that have maybe failed to remove themselves from orbit, maybe due to a propulsion failure or a communications failure, or something that's run out of fuel. Now we have the ability to remediate that issue because we can go up and dock with it and bring it out of orbit. We can also extend the lifetime of assets in space. So some satellites have a specific amount of fuel on board. And once they run out of fuel or get down to a small amount, then they have to end their mission because they have to use that fuel to get themselves to a disposal orbit and then passivate the spacecraft. But maybe let's say the payload hardware, the instruments on board, are in perfect working condition, and that spacecraft is still providing good science. Well, if we can't go service it, we have to retire that spacecraft. We have to launch a new one. And so that is, we're putting more spacecraft in orbit. It's just not as efficient. So if we extend the lifetime of a satellite, we are reducing the amount of potential space debris that we are introducing to the environment. So these are more sustainable behaviors. We think it leads to a more sustainable environment long term because we're reducing that risk. We also think it's going to open up new doors for new types of industry in a couple ways. One is through the servicing and space logistics, the ability to move from one asset to the other and manipulate or assemble something or transport is going to, I think, unlock some interesting new space applications. And also the ability to service something or refuel it or change something on orbit. If we can do that cost effectively, it should also lower the cost in terms of the cost of entry into space. Because again, in the past, you want to design something that's going to work no matter what for 20 years. So you have to have extremely high reliability on the systems that you're designing. It needs to work in all these corner cases, redundancies built in, just because there's nothing you can do if something goes wrong, and you don't want to lose your $100 million asset or $1 billion asset, or several billion if you're working on the JWST. So if we can rely on on-orbit services to maybe fix that problem, now that could lower the cost of the spacecraft and reliability that we're building into our platform before launch. So that's what we're focusing on at Astroscale. So we're built on this shared vision, the safe and sustainable development of space for the benefit of future generations. This vision and our mission is a shared passion between our team. It's actually really great to be part of that. And we found a lot of people who want to join in on that mission. And so we have offices in 5 different locations. Started in Singapore actually in 2013. But our headquarters now are in Tokyo. And that's where I'm based currently. We also have offices in Harwell in the UK, Denver and DC, and Washington, DC, sorry, in the US. where DC is focused on more policy efforts, and Denver is working on a life extension. And then we have an office in Tel Aviv, Israel, as well. So we have global distribution. We have, I think, around 240 employees now globally. And we've raised private capital of 190 million. It's just, I think it's really exciting to see that other people share this passion. They want to contribute to sustainable development. They see it as really what the future is. So Astroscale is focused not only on the technical solution, but also the business case and the policy framework that needs to be put in place. Right now, in-orbit servicing, or the ability to dock with another spacecraft and move it or perform some service, is not, current regulations and frameworks are not really conducive to that activity. So there's a lot of work that has to be done to reshape what the policies are. I think a lot of regulators aren't used to spacecraft getting so close together and doing something constructively. So there's a bit of a hesitance for regulators to embrace this new idea. So we're working closely with regulators worldwide. I think everyone wants to see it happen. It's just regulation moves extremely slowly. So we're helping that process along. And then there's the work that's being done on the business development, because this is a very new type of service. It's a new market. And without a business case, it's hard to make this a sustainable way forward. If responsible behaviors and sustainability are seen as an expense only, I think it makes it much harder for that service to thrive. We don't want to be a service that is only there because regulations necessitate it, because it becomes more like a tax and a nuisance. But really, we should be seen as an investment in the future. So operators who have large constellations want to keep their orbits clean of space debris, as well as the orbits of nearby operators, and the ability to better manage their constellations and make use of assets that are in space already, because that launch cost can be so great that once you have something in space, if it fails or has a shortened lifetime, if there's some way to utilize what you've already put in space, then that helps your overall business case as well. So again, we're helping to develop those business cases, and this will create this ecosystem where in-orbit servicing is seen as commonplace. That's kind of our goal. I liken it to SpaceX launches. They were exciting a while ago, but now they happen so frequently that they're still cool, but it's like, okay, this happens so often that it's not maybe as novel or interesting as it was before. And so our goal is that servicing missions, when we have one spacecraft that grabs debris or docks with another spacecraft, that is so commonplace that it doesn't really seem that special. So that's our vision. And so to achieve that, we're looking at 5 core services that we're developing. It's a life extension. Right now, that's focused mostly on GEO, because in geosynchronous orbit, it's more expensive to access that orbit, and frequently those assets are much more expensive than what you see for spacecraft in LEO. So extending the lives of those spacecraft that represent a significant amount of investment, there's a strong business case for that. We may see life extension in LEO orbits as well, but those will be for much larger platforms, typically coming from more government applications. There's in situ SSA, or inspection. SSA is space situational awareness. So this is the ability to rendezvous with some object, orbit around it, take pictures, and gain information about the condition of the object. What does the surface look like? Is it tumbling, etc.? What are its properties? Orbit transfers, that's pretty straightforward. You just grab onto something, bring it to a new orbit, change its inclination, bring it back down. Active debris removal and end of life are actually very similar. They're both services built around taking something that is no longer useful and bringing it back out of the space environment so it's no longer a risk. The difference is that debris we consider to be something that is has been launched and it was not envisioned for servicing. So there's no preparation done. There's no known interface that is conducive to servicing. Whereas end of life means that the operator thought about this ahead of time. So they put a mechanical interface, a docking plate, some laser reflectors on it in preparation of future servicing. And this helps lower the cost and complexity of a servicing mission. So that's what I'm going to talk about more as the end of life service, because what Astroscale is doing right now is demonstrating some of the capabilities that are directly applicable to end of life service. And that is with our ELSA-d mission. So ELSA stands for End of Life Services by Astroscale, and the dash D is for demonstration, because this is a self-funded demonstration mission right now. And it's really the first mission of its kind to do this end-to-end demonstration of all the technologies that are needed for end-of-life services. So this is an actual picture of the hardware before we launched it. We launched it in March. And so in this stacked configuration you see on the slide here, it's actually two separate spacecraft that we launched together. And we launched a servicer and a client. And the client is representative of a spacecraft at the end of its life that has prepared for removal. Yeah, so just some details here. We built this in Japan, but it's operated out of our offices in Harwell, just down the road, basically. It's actually a bit of a hike to get from London to Harwell, but so this is just a drawing, drawing of the spacecraft in its separated configuration, just to see it in action here. So you can see that the servicer spacecraft is equipped with a sensor suite that allows it to do its rendezvous mission. So we're using a combination of visual cameras, IR, laser rangefinders, so we can see the client and we can safely approach it and then assess its state of motion. And the idea is that once we have a good idea of where the object is and what it's doing, we locate its docking plate, which is it's shown on the right there. It's this circle right here is a ferromagnetic plate, and the dots that you see on it are optical fiducials that help guide us in. Once we locate that, we can zero in our relative motion using the propulsion system on the servicer spacecraft and safely contact it with this extended magnetic capture system on the servicer. We chose magnetic because it allows for not a lot, but a good amount of tolerance, error tolerance in the final approach and the contact. So we can come in with a slightly misaligned angle or a linear or axial, linear displacement and still have safe contact. It's also an inelastic collision, which is a potential problem for just a mechanical docking interface. If you have contact and you miss, it could introduce some dynamics to the system that will be hard to control. There are other concepts like nets and harpoons that are out there, but the chaotic nature of that tethered connection is, I think, a significant risk in taking safe custody of an object. Once if you harpoon it, it's going to introduce all these dynamics that are difficult to control, difficult to predict. The last thing you want is for your servicer to contact the client and create more space debris. All right, so a little bit more detail about the mission profile that we're currently in the midst of. All right, so we already gone for our lunch, our launch, and our commissioning of the spacecraft, making sure everything's checked out and working fine. And then in August, we did our first test. And that's where we released the client from the magnetic capture device. And then we used our servicer to then dock with and capture the client. And that was successful. Pretty excited about that. And I'm pretty confident that's the first time anything like that has ever been done in space, at least from a commercial company, to capture an uncontrolled object like that, especially with magnetics. So it was very exciting for us, a really key demonstration for our capabilities. The next phase that we'll go in is that we're going to separate the client even further and do a few more assessments with our instruments on board, such that we have a good idea for how to understand the dynamics of the client. The first test we separated, it wasn't very far, and we did some testing with our sensors, but we weren't doing the full operations that we'll be doing phase 3B. In phase 4, we're going to do this similar activity, but we'll actually put the client in a tumble, and that will simulate, most space debris up there, because space debris is not controlled, and through solar radiation pressure or failure modes, most of space debris is expected to be tumbling about at least one axis. It can be quite unpredictable. So our servicer has to be able to assess those tumble rates and put itself into the right motion, which we call a dance. So it kind of dances with the client, make sure it has zero relative motion before it makes contact, because that's the safest way to capture. Phase 5 is we're going to release the object and separate at a significant distance, and that is to simulate using our onboard instruments to locate exactly where the object is. With space debris or a failed spacecraft, we will have ground-based measurements of where the object is. Ground-based radar can track where it is, and the problem is that data is not always precisely, it's not, there can be errors of kilometers sometimes in the orbit prediction, especially several days out. And so we're going to be using that information to create our rendezvous strategy to get to that orbit. However, we have to accommodate a large amount of uncertainty, which means we have to have very safe distance in our approach, because it could be anywhere within a certain error ellipse. And so once we get to that phase, we switch from an absolute navigation mode that is based on ground measurements, and we go to a relative navigation mode using our onboard sensors. So we locate it, and then we go into a different rendezvous phase of the mission, where we're using a variety of sensors as we get closer and closer to get more confidence in the position of that object. Then at the end of the mission, we lower our spacecraft to decrease the risk that's opposing to the environment, and then it will eventually burn up in the atmosphere. There's a bit more detail about exactly what we did with our test in August. So what we proved with that demonstration is that we can use our magnetic capture device with the docking plate, a ferromagnetic plate. Demonstrate docking and undocking between the two, because we need to have a system that is not permanent. We can dock and redock and undock as many times as we need to, because we want to have a service where we can address multiple clients with a single spacecraft. So that's a key capability. We've calibrated our instruments and sensors on board. A big part of this mission was proving out our ground operations capabilities. So we have our main operations center in the UK, and that's where the effective control is. The UK sends all the commands, all the telemetry comes first to the UK. We also have an operations center in Japan, because that's where the spacecraft was built and integrated. So a lot of the the key engineers are based in Japan. So this activity was a very coordinated operation between our global offices to make sure that we do this in a safe way and have the best information available to assess, can we go ahead with the mission? Is it successful, etc. And yeah, the validation of our procedures that we develop. Again, because this has never been done before, so this is pretty critical to work through our first time, and that's why we're taking this in phases to make sure we gain that confidence. We find out where there are issues in the process. What do we have to refine? What do we have to get better at? That reduces the risk of going to the next phase and doing something more sporty. So as I mentioned, we need to get to this, to have this a sustainable, successful commercial service. We need to have a servicer that can address multiple clients. ELSA-d, the demonstration, was really only built to do this with one client and then end of mission. But we are currently transitioning from ELSA-d to ELSA-m, where the M stands for multi-client. And so we're developing this with a public-private partnership with ESA and OneWeb to turn this into a commercial service where we could address, 2, 3, 4, or more clients in these constellations with a single servicer. And that means we're getting more use out of each servicer, and it reduces the overall cost of the end-of-life service. And yeah, the key is also to make sure that this servicer can address a wide variety of clients, because you don't want to have a custom servicer for each spacecraft that you want to service, because that redesign, the engineering work that has to be different for each client translates to a higher cost. So if you can have one universal servicer that can serve any large constellation operator, then you have more modular, scalable, and lower cost system. It's always a unique challenge with spacecraft to have something that is modular, and eventually you're going to come up against some constraints where your system is no longer able to serve some of the outliers. But it's about choosing that right circle to draw around the right size of the market, and that's what our team has been working on quite a bit in the UK. Okay, so the end-of-life service sounds good, and ELSA-d is using magnetic capture, but that only works if the client is prepared with a ferromagnetic docking plate. And traditionally, actually, a lot of spacecraft avoid ferromagnetic materials. That's because they interact with Earth's magnetic field, they interact with magnetorquers that are used for attitude control, and they can have a dipole. They can retain a dipole that will interfere with your magnetometer. So most of the time, you try to limit your ferromagnetic material that you use on board. But this is actually my previous work at OneWeb was actually working with these docking plate suppliers to make sure that what is created as a docking plate has minimal amounts of interference. So it's a very particular material, ferromagnetic material, that minimizes the remnant dipole, and it's you make sure you're not putting it next to any sensitive components. So in some cases, it does require a little bit of accommodation for the client, but mostly it's a passive, unobstructive docking plate that's trying to keep this low mass, so less than ½ a kilogram. And the idea is that operators can put this on the spacecraft at very minimal impact, and now they're prepared for the future. It's a backup plan. If they ever need to service their spacecraft or remove it, they have this option on board that will reduce the cost of the service that is provided. And OneWeb has embraced this already. You can see the picture of spacecraft being integrated for launch. They have a docking plate, and this the fiducial that is on board is something that Astroscale worked on. The hardware itself comes from a company called Altius Space Machines, but it's it's compatible with our servicer. And OneWeb for a while was kind of an outlier, but we're starting to see more and more operators embrace this philosophy. So Lockheed Martin said that their GPS satellites are going to be prepared for in-orbit servicing. ELSAd, the light speed constellation that they are working on, they haven't decided exactly what the interface looks like, but they have a spec that their spacecraft need to have some sort of feature that enables servicing. So I think we're seeing this transition where operators are starting to look less at this one and throwaway culture of their spacecraft and thinking about use cases that will be beneficial for their costs, but also more sustainable at the same time. So we're really excited to see that this trend is catching on. This is just the last slide to look at some of the other activities we have going on at Astroscale. Life extensions primarily done out of our US office with technologies that are being developed out of the Israel group. They're doing the docking mechanisms. ELSA-d is our current mission that will be soon transitioning to ELSA-m as we take this to a commercial model. In Japan, right now we're focusing on the ADRAS-J mission. This is a mission that we won from JAXA. So JAXA has contracted us to do the first of 2 missions. So it's the first phase of a 2-phase mission where the ultimate goal is to remove a 3-ton upper stage of a rocket body that is just derelict in space. So phase 1 of the mission is to rendezvous with this, take pictures, see how it's tumbling, basically gather intel that will help us design the next phase of the mission, and that's phase 2, which is actually to grab it and then bring it down out of orbit. So really excited about that. I think there are a few missions being worked on within Europe that are targeting kind of 100 to 200 kilogram class objects, but this is going to be the first 3-ton object, which is, if we had to focus on one thing to remediate debris in the environment, we want to focus on the more massive objects. So this will be a really good step, I think. So yeah, that's it. That's the presentation. So thank you very much, and I'd love to take some questions. And there's my contact information if anyone is interested in reaching out.